This is another example where we can apply Coulomb's law along with theories that we learned about circular motion back in General Physics 1. The first thing I'm going to do is draw the forces acting on the particle that is of concern. So, if we read the question, it says that there's a charge with a negative charge, Q minus Q. So that is this particle over here. And it has a mass M. And it is moving, it is executing circular motion, uniform circular motion around this fixed charge, which is placed at the center. And that has a positive charge, plus uppercase Q. The radius of the circular track is given as R, and when the charge that is moving around, when it's executing these circular motions, there's going to be a time period for it. We want to calculate that time period, and we want to actually show that time period to be equal to this algebraic expression. So there's no numerical values here. It's just a symbolic algebraic expression. That's what we need to get. So the first thing I'm going to do is draw the forces acting on this minus Q charge that is moving in the circular track. Now we are going to neglect any type of gravitational forces between these two charges. Even though you can see the mass is given for the charge that is in motion, there's no mass given for the charge that is at the center. So we are going to neglect the gravitational forces between the two charges. So that's an important thing. If it's not stated, then we can consider that. We will neglect gravitational forces between the two charges. So that's an assumption that we are going to make. Unless you are given consider gravitational forces, you don't need to use that. So the only force as a result are these electrostatic attractive forces. So this plus Q charge at the center will exert an attractive force, an attractive electrostatic force towards the center in this direction, and that's what we call this Coulomb force or the electrostatic force acting on this charge that is moving. According to Newton's third law, this moving charge is also going to exert a force on this stationary charge. So that's going to be in the opposite direction, like that. So both are equal in magnitude. They're acting on different objects, different particles, and they are aligned in the opposite direction. One is towards the center, the other one is away from the center. So these two forces, we call it an action-reaction pair, a Newton force pair. Okay, so now we are ready to apply theories in circular motion to figure out this time period. So let me do that now. So if we consider a motion along the center, motion towards the center, the center of this circle, then we can apply Newton's second law, F equals ma. F is the net force. That means the sum of all the forces in that direction towards the center equals mass, that is the mass of the particle that is moving around this circular track. So that's this particle. We are not going to consider the particle that is at the center, okay, because our system is this moving particle times what is the acceleration towards the center. We call it the centripetal acceleration, AC. Okay, so remember, AC can be written as speed squared divided by the radius, that is the distance between these two particles. Or else we can write AC as omega squared r, where omega is called the angular frequency. Angular frequency. So if you took General Physics 1, then you should have done these things in that course when you consider motion. So again, there's a connection between omega and the time period. So I'm going to use that connection. As a result, I'll be using this expression for AC. You might think, okay, there are two variations for AC, V squared over R or omega squared over r. Why am I going to take omega squared over r? You will see that I'll be taking omega squared over r. M omega squared times r. It's not over, it's times r. Why am I selecting this? Because I can write omega in terms of the time period. Omega is 2 pi over t. So this is again from General Physics 1. As a result, that's why I'm going to use this expression instead of this one, because it directly connects me to time period. Okay, now the net force is simply the electrostatic force, and since we are looking towards the center, this force is towards the center, so that's the positive direction. So I'm just going to write Fe. So that's Newton's second law applied for this electrostatic charge that is moving around the circular track. Now I'm going to explicitly write down Fe using Coulomb's law, and omega, instead of omega, I'm going to put 2 pi over t. So Fe, as you know, the magnitude of this force, so this is just the magnitude, is equal to K times the magnitude of this uppercase Q times the magnitude of the minus lowercase q charge over the separation between the two charges, which is r, but we have to square that, r square. So I'll simply substitute that over here. The negative sign falls off because we are just considering the magnitudes. So I'll have k q over r squared, and then I'm going to make the substitution for omega. Omega is 2 pi over t. I square the entire thing times r. Now I need to solve for the time period, or t. So now the physics is done. So now I am going to use some algebra to simplify this expression. So I'll notice that there's a t squared in the denominator. I'm going to take it to this side, and I'm going to solve for t squared. So then in the numerator, I can take this r squared over there. So then multiplied by this r, it will become r cubed. So I'll have 4 pi squared m times r cubed. And then in the denominator, I'm going to have k uppercase q, lowercase q. Okay. Now I need to make one final substitution, since k is equal to 1 over 4 pi epsilon naught. I'm going to make that substitution. So in the denominator, if I write 1 over 4 pi epsilon naught, you can see the 4 pi epsilon naught term goes to the numerator. Okay, so then I can write this as t squared equals 4 pi squared m r cubed times that part that came from the denominator, 4 pi epsilon naught, and then over q times q. So now I can rearrange. So I think I have everything here. Now I'm going to take the square root. The square root would be the square root of, there's a 4 and a 4, so that would be 16. There's a pi cubed, so I'm going to write that pi cubed over here. And then there's this epsilon naught, the permeability of free space. And then the m, the mass of the particle that is moving in the circular track. And then finally r cubed, the separation between the two charged particles, or the radius of the circular track. And then I'm going to divide this entire thing by the product of the two charges, uppercase q times lowercase q. So that's how you get this algebraic expression for the time period. Now you can see there's no numerical substitutions for this one. We just ask you to figure this out. So this is a very good question for multiple choices. We can give you different variations or different algebraic expressions for t, and then we can ask you what is the correct term. So in certain terms we'll have r cubed, r squared, r to the power 4. There will be certain changes here, and then we'll ask you figure out the correct expression. So then you have to do this step by step algebraic simplification, get this answer, and then compare with the multiple choices given. Then you can select the correct choice.